So now we can do example 6, classify, right? These are 4 equations, the general form, right? They're not they're not in any standard form for you to recognize, but by the pattern and what we just got, for example, on the first one, it looks like A is 4. What is C? 0. There is no y squared. Which one of them has only one squared term? Go back and look. You just wrote it down as a note. So which one of them is one of those equal to 0? Parabola. Right? Because only one squared term right there. Okay, the next one, A is 4 and C is -1, right? Which one is it? Hyperbola, they have opposite sign. Okay. All right, the next one, A is 2 and C is 4. They're both positive. Which one is that? Ellipse, right? Ellipse, they're not equal, but they are the same sign. Ellipse. And the last one, A is 2, C is 2. Which one of the 4? Circle. So there's like 8 homework problems like that, but all you have to do is say the word. There's nothing else to do. Yeah? The parabola and the hyperbola? If it only has one squared term, that's a parabola. Either A or C is 0. In this case, C is 0 because there's no y squared. Right? For a hyperbola, they have opposite signs. One's positive, one's negative. Now, I'm going to say just a couple of things about this because I took out the one that said we're going to do real life problems with this. I mean, it's not that there isn't some real life stuff that goes on with hyperbolas. Hyperbolas are used in navigation. There is an example that they give, which is a little bit interesting, but it goes something like this, right? That if you, they have like 2 listening stations, and if you hear a noise from both of them, then because the sound gets to you at 2 different times, you can figure out like what's the difference in the time for you to have gotten them. That is the knowing that distance, the difference and when did I get the sound from that one or hear it at that station and that one helps you to locate yourself on one branch of a hyperbola, right? Remember that the difference of the distances is constant. So once I've got that constant, which is that difference, I'm able to locate myself on a hyperbola. Now, in that example, it's not like they could say exactly where they were, but they could say it must be somewhere along that branch. And I'm pretty sure, if you remember when that Malaysian airliner went disappearing and they were like really trying to figure out where was this thing, at one point they were showing arcs that looked kind of like a hyperbola and saying, we don't know where, but it's got to be somewhere along this arc. And I don't know for sure that it was hyperbola, but it could be like that they detected the signal from 2 different satellites and were able to do that difference formula to say, okay, that means it's somewhere along there. So that is one place that you use those. This used to be something that was kind of like integrated into the navigation systems that the Navy would use. In the old days, people were all actually sitting down doing calculations with hyperbolas. These days, I'm sure it's all computerized and they don't need it. Another thing that they talk about, and this is at the bottom of 718, is that actually comets have orbits that are either elliptical, parabolic, hyperbolic, right? I mean, the thing about a parabolic or a hyperbolic orbit is once you see the thing, you're never going to see it again because it's not coming back, right? Ellipse is the only one that it's making a path that actually will repeat itself. Like the one comet, which is the only one anybody can ever name, is Halley's Comet. And that was one that, they saw the orbit, and then they used that to predict when it would come back around again. And they were accurate. I mean, I think that was using 1800s calculations. And they got it pretty much exactly right using prediction.